In this podcast, we're going to go over intermolecular forces. We're going to talk about those interactions between molecules for liquids and solids, and then we're also going to go into some properties that are specific just to liquids. When we talk about intermolecular forces, we are talking about the attractive forces that holds two molecules to one another. So when we talk about gases, we don't really talk about attractive forces because those gas molecules are farther apart than each other. They may not be interacting as much. So any interactions between molecules tend to be minimal just because they spread out to take the volume of the container they're in. But in solids and liquids, your molecules are a lot closer together. And those interactions we do consider to see which have stronger or weaker interactions. In ionic compounds, you have a positive charge and a negative charge, and having elements within a compound having those charges results in a lot stronger attractive forces between your compounds. So if the force is stronger holding two compounds together, it's going to take a lot more energy in order to break those bonds and to get those molecules to separate from each other, or for instance, on a bigger scale, to move from a solid to a liquid or a liquid to a gas. Therefore, because of all the energy it takes to separate those molecules, you're going to have a higher melting point or a higher boiling point. So let's shift our focus now to the attractive forces that hold covalent molecules together. In covalent compounds, there are several types of attractive or intermolecular forces that occur between molecules. All of them are considered to be weaker than ionic bonds. All right, so the first one, the weakest, is the London dispersion force, and these are weak attractions that are present in nonpolar compounds. So all covalent compounds have London dispersion forces. Again, it's the weakest intermolecular force in covalent molecules. So if you have a nonpolar covalent molecule, say for example you have, let's see, this image is showing us methane. So let's go ahead and draw methane, which is CH4. Okay, so notice that your carbon-hydrogen bonds are all nonpolar. So the molecule itself is nonpolar as well because there's no polar bonds. There's equal sharing of electrons. So the only force that's present in a nonpolar covalent compound is going to be London dispersion forces. The larger the molecule is, the larger the force, the stronger the interaction. So when you think about the size of a molecule, say for example, argon atoms versus helium atoms. Argon's much larger, therefore the force is stronger, so those are held together tighter, and in order to separate them, it would take more energy. All right, so the way London dispersion forces work, because there is no polarity, is you have this assumption that you have these electrons floating in your electron clouds. So you have pockets potentially, and we're just assuming, as these electrons are floating around at any given point, you may have a bigger density or a more dense area on one side of the electron cloud that has more electrons in it, just temporarily speaking. And then on the opposite side, you have another side that has more positive, and those don't last very long. They're temporary because your electrons are moving. So the force, this slight positive and slight negative, as you can see right here, that attracts two different molecules together is the result of a temporary dipole that's created. So temporarily, the electrons just happen to be more dense on one side, creating a slight negative charge. So it's a very weak, because it is fleeting, a very weak attractive force. All right, so we've already established that London dispersion are our weakest forces, and those are between non-polar molecules. The next type of force, which is a little bit stronger than London dispersion, are dipole-dipole interactions. Dipole-dipole, I'm going to add to my list. These occur between polar molecules. So you have to have unequal sharing of electrons in order for them to exhibit a dipole-dipole interaction. So on the big list of things, these are stronger than the last slides, stronger than London dispersion forces, but they're weaker than hydrogen bonds. So the reason that they're stronger than London dispersion forces is because they have what we call a permanent dipole. So let's look at formaldehyde. Formaldehyde has polarity in the bond between carbon and oxygen. Oxygen is more electronegative, so it pulls the electrons closer, taking on a slight negative charge. Carbon is slightly positive because it's losing that tug of war. It's further from those electrons. Well, that slight negative charge is still a negative charge, and that slight positive charge is still a slight positive charge, and those two are attracted to each other. So that difference in charge that's permanently there, it's not fleeting, it's not temporary like it is in London dispersion, but those attract those molecules together. So it's going to take more energy to separate those two molecules than, say, it would in a London dispersion force. All right, so our last intermolecular force is hydrogen bonding, and this is where you have a hydrogen bonded to a highly electronegative atom, and it's specifically these three. So you can have H and N, H and O, H and F. The way I remember this is hydrogen bonds often. Often, OFN. You may come up with a better way for that. I don't know. So what we have is a really big difference in electronegativities between hydrogen and nitrogen, probably the biggest difference you can have without it becoming an ionic or a full transfer of electrons. So we have this dipole that's created. And so same idea as last time, you have a slight negative charge on oxygen and a slight positive charge on hydrogen. So what you wind up with when you have a lot of these molecules together is you have all of your slightly negative oxygens wanting to be close to all of your slightly positive hydrogens. So they orient themselves so that you have those opposite charges together. And just like in a dipole-dipole interaction, opposite charges are keeping those held together, but because of the difference in electronegativities, hydrogen bonding with oxygen, fluorine, or nitrogen is a lot stronger than any other dipole where you don't have those molecules together. So because of that, anything that exhibits hydrogen bonding is going to take a lot more energy than dipole-dipole interactions, a lot more energy than London dispersion forces in order to separate those molecules. So as we kind of alluded to, the stronger your intermolecular force, the higher your boiling and melting points are. All right, so the way this works is you start with your London dispersion forces. So these are your non-polar molecules, and these are going to be very weak temporary dipoles. And then your dipole-dipole interactions are with polar molecules, so you have a permanent dipole where you have that slight negative or slight positive. And then finally, compounds that can hydrogen bond are going to be the strongest of all of those forces. And part of it has to do with the fact that all covalent compounds at least have this. If you have a polar compound, you are going to have London dispersion forces and you're going to have dipole-dipole. So you actually have two forces at work, which makes it a lot stronger and a lot more difficult to separate those two molecules because they're stuck together. And finally, think of this as a cumulative effect. If you have hydrogen bonding, you have London dispersion forces as well as your dipole-dipole interactions on top of your hydrogen bonding. So that is going to increase your boiling point and your melting point for that molecule. All right, vapor pressure, we're talking about liquids now specifically. Vapor pressure is the escaping tendency of molecules, which is a little bit vague. When we talk about vapor pressure, we have to first talk about evaporation, which occurs when your liquid molecules are going to escape the surface to become gases. So these molecules that are on the surface tend to have more energy and they're able to more readily escape to the gaseous phase. You will absorb energy. This is an endothermic process to go from liquid to gas. If you have an open container, say like you do, we're just going to pretend her bottle's open, eventually all of these water molecules are going to escape as a gas. However, in a closed container, it's a little bit different. So in a closed container, you do have these surface molecules escaping to the gaseous form, but they're turning into a gas and they're stuck in this closed container. As more and more gas molecules accumulate, you're eventually going to get some molecules that are re-entering the liquid phase. You have some evaporating, going into gas phase, and then you have others coming from the gas phase, condensing again and becoming a liquid again. So you kind of have this equilibrium going on. At equilibrium, you're going to have the rate of molecules escaping as gas at the same rate as you have molecules condensing to a liquid again. I know we don't have notes on this, but it's worth mentioning. So if you have stronger intermolecular forces like you do with water, which is going to have hydrogen bonding, it's going to take a lot more energy in for these liquid gas molecules or liquid molecules to escape as a gas form. So you're going to have a lower water lower vapor pressure because of that. But if you have something, say, like methane, which exhibits London dispersion forces, which are weak and they easily escape from liquid, or they change state from liquid to the gas form because it doesn't take much energy, you're going to have a higher vapor pressure. So you're going to have a lot more gas molecules that are escaping as gas because it doesn't take as much energy for them to change state because of their forces. All right, so let's continue our talk on vapor pressure. As you increase temperature, your vapor pressure also increases. So when you increase temperature, you're actually increasing the movement of the molecules, and the more they're moving, the more energy they have. When your temperature gets high enough that your vapor pressure above the liquid, so your vapor pressure above the liquid is equal to the atmospheric pressure, even molecules below the surface are going to have enough energy that they're going to start escaping to the gaseous form from liquid. We call that boiling, and that would be the boiling point. So your boiling point is also related to the atmospheric pressure. So when your vapor pressure is equal to the external pressure, okay, so your vapor pressure, that's the pressure above the liquid, is equal to the external pressure, which at sea level is 1 atmosphere. You're going to get all of that liquid trying to escape into the gaseous form. At higher altitudes, we have a lower atmospheric pressure because your vapor pressure has to equal the external pressure to boil. If you have a lower atmospheric pressure, it's not going to take as much energy to get that liquid water to boil. So your boiling point is going to be lower, which is what we see here. Denver, which is a mile above sea level, is around 93 to 95 degrees Celsius, which is lower than our standard at sea level 100 degrees Celsius. So the stronger your intermolecular forces, as we showed on the last slide, the lower your vapor pressure, because it's going to take more energy in for those liquid molecules at the surface to escape as a gas. Some other terms we use to describe liquids are viscosity, and this is a measure of the fluid's resistance to flow freely. If you have stronger intermolecular forces, your molecules are going to be drawn together. They're not going to flow as freely, versus if you have weaker intermolecular forces like London dispersion forces and nonpolar molecules. Also, the size of the molecule is going to play a role in how viscous or how thick a molecule or a container of molecules is. The larger the molecule, the more difficult it is for those molecules to slide past each other, which is also going to provide resistance for those molecules to flow freely. So I like to think of water compared to gasoline. Gasoline has little to no resistance to flow freely, whereas water does. And then olive oil, being a very, very, very large chain of carbons and hydrogens, is a lot more viscous. It's a lot thicker. It doesn't flow as freely. Another term we describe when we talk about liquids is the surface tension of a liquid. And this is a measure of the resistance of a liquid to spread out. So to talk about this, let's look at this image. When you're talking about water, just say water in a container, you have water on the surface, which is this image, and then you have water down below. So when you have a molecule right at the surface, you have interactions between this water molecule and all these other ones below it. When you're talking about a water molecule in the center of the beaker, it has intermolecular forces working on all sides of it, not just right at the surface and below. The stronger the intermolecular forces are, the more they're going to pull down on these surface molecules and hold them intact. And the stronger your intermolecular forces are, the stronger these surface molecules are pulled down toward the interior of the liquid, and therefore the higher your surface tension. So it's not able to spread out as well. This is why when you see a drop of water on the countertop, it tends to take on a bubble shape. All of these surface molecules are being pulled inward and being pulled down. Whereas if you had I don't know, like you spilled isopropyl alcohol, there's not as strong of forces there that are pulling it inward. So it's not bubbling up. It doesn't have as good of a surface tension. You are looking at water, which has a very high surface tension in this image that allows a water strider, which I always used to call them Jesus bugs because they walk on water. It allows it to walk on the surface of water due to all those strong hydrogen bonding, those intermolecular forces between the water molecules.